OK。So 那个跟大家提醒一下哦，那个我们下礼拜就期末考，你们知道哦。下礼拜有期末考，所以那个sample final 我有放在那个e-class 上面了。OK， 请同学可以看一下。OK， 那题目不会一样啊，但是那个至少你可以看一下那个出题的那个类型，这样子，好不好？那所以请同学记得哦，就是下礼拜。下礼拜几号是25号，对，25号起，这个线性代数的期末考 ，OK， 好，那 OK，let's come back to this. We still have like about 20 minutes. Okay, so the next topic is similar matrices. Okay. So let A and B be n by n matrices. If B is similar to A, then two matrices both have the same characteristic polynomials, and consequently, both have the same eigenvalues. So do you remember what I mean? What does that mean? Like two matrices are similar. If A If A and B are similar, okay, it means like B it means like it means that B equal to S inverse A S. Okay. There's another matrix B exists, okay, such that B equal to S inverse A S. Okay. So here we want to show that okay the eigen the characteristic polynomial of these two of A and B are the same. So we write it, okay. The polynomial B lambda equal to the determinant B minus lambda I, okay. And we know B equal to S inverse A S minus lambda I, right? And then okay, I can be written as S inverse times S, right? Okay, so you can get S inverse out in the front, and get S out at the back, so it becomes A minus lambda I. Okay. In the front we have S inverse, in the back we have S. Okay, you become from here we get this. Okay, and then okay, determinant of A times B equal to determinant A times determinant B. Okay, if A, B are square matrices. Okay, so we have that. So this one becomes this one times this one times this one. But because determinant S inverse and determinant S, they multiply to be to be 1. Okay, so it means so you'll be like this, and it will be PA lambda. So PB lambda equal to PA lambda. So in other words, since their characteristic polynomial are the same, so they have the same eigenvalues. Okay, they have the same eigenvalues. So that's the end for the first section. Okay. The second section is about linear differential equations, which will not be covered. Okay, we will not cover linear differential equations. I mean, it should be covered by 工程数学英文怎么讲？你们修过了没有啊？工程数学修过了，这学期修，上学期修。事实上，我觉得工程数学应该是晚一点来上啊，应该是讲好说线性代数应该要早点上，应该线性代数你们大一上，工程数学往后面是。但 you know I'm not the one okay to design the curriculum okay yeah 将来有机会我可能也会有可以讨论这个东西，但是现在还就说不会去改变这个。但是有一些东西应该是在你们工程数学教，像这个微分方程哦，这个应该，你们微分方程有在你们工程数学教吗？有吧 ？OK， 那就好。好，这个我就不会跳过去，我有 slide 啦，我有 slide， 真的要教我可以教，但是我觉得说我们就对啊，就跳过去好了。Okay, diagonalization. Okay, diagonalization. Okay. So an n times n matrix A is said to be diagonizable if there exists a non-singular matrix X and a diagonal matrix D such that X inverse A X equal to D. Okay. We say that X diagonalizes A. Okay, so this is a little bit similar to like two matrices are similar, but it's about diagonalization. Okay, so this is a definition. So there's a theorem: an n times n matrix A is diagonizable if only if A has n linearly independent eigenvectors. Okay. So here's the thing. Let me think. We know like AX这个好像也不太行，这个嘞 ，OK。We know that for eigenvalue, for eigenvector, okay, okay. let's say we have this n independent eigenvectors. We know a v1 equal to lambda 1 v1, right? A v2 equal to lambda 2 v2. A vn equal to lambda n vn, right? Right? We have this, right? They are eigenvectors, so they have like corresponding eigenvalues, right? So far so good, right? Right? Okay. Then think about this. Oh, by the way, this lambda I, some may be the same. Okay. We know different eigenvalues, their corresponding eigenvectors are independent, right? We proved that previously already, right? But for independent eigenvectors, their corresponding eigenvalues may be the same. Okay, it's like one-way direction. Okay, the other way back may not be the case. Okay, just want you to be aware of that. But that's fine as long as lambda I are not 0. Okay, as long as lambda I are not 0, so that's fine. So we know that. So let's now consider this. Let's try to make this as v1, v2, vn. Okay, we try to let this vi to be the ith column vector. Okay, we have n columns, right? So you just let this n eigenvector to be like their n columns. Okay, and then okay, this one will be what? This one will be lambda 1 v1 lambda n vn, right? Right? So far so good, right? It's just like we try to abbreviate it. I mean, originally we have like n equations. Now we abbreviate this n equation into like the matrix multiplications, right? So this is, we let this one to be x. Okay. And then this one will be, out of space. Let me write it here. This one will be v1 vn times x1, lambda 1, sorry, 0, 0, 0, 0 lambda 2, 0, 0 lambda 3, okay, lambda n. These are all 0, these are all 0. And, if you multiply this one with this diagonal matrix, we get this, right? Right? So we just name this one to be D. And remember, we name this one to be X, right? So this one is X. This one is X, this one is D. Okay? So let me write it again. So we have AX right? Where X is composed of like n column vectors, okay, each coming from the eigenvector. And the D is the diagonal matrix, the diagonal elements represent the eigenvalue for the corresponding eigenvector. Okay, if you have that, then obviously, you know, because X is like we also know like because X these eigenvectors are independent, right? So in other words, for this square matrix, its rank is n, right? So it means it's non-singular, right? If it's non-singular, its inverse exists, right? Okay? Because X is formed by n independent column vectors. So X must be, you know, invertible. Okay, so you multiply both by X inverse. So we know we have so we have X inverse AX equal to D. Okay? So this is if and only if, right? If and only if. So actually, okay, the whole process can be, you know, reversed, going backward to the original place. Okay, so if there exists, you know, if A, you know, if A is diagonizable, okay, that means there exists X inverse X such that X inverse A X equal to D, right? Okay, in other words, X is non-singular, right? So you just treat each column vector, each column in the X as like a column vector. Okay, and then from here you get this, right? And from here, I mean, and if you examine each you know, column in XD, that means like you know, it's scaled, right? That, I mean, corresponding vector is scaled. So that pretty much means like each of them represent like a eigenvalue and eigenvector. So we go back to the original one. Okay, so basically this is like you know, diagonalization. Okay, so well, I think like yeah, for this example, I think you guys can try to do it yourself, because like you know, basically you try to compute the characteristic polynomial, and you get like you know, different eigenvectors, and you also have to check if these three eigenvectors are independent, but most likely they are. Okay, I don't have time to do that, so you just let X to be this. Okay, this X is not unique. Obviously, you can permute. It's the order of the column, obviously, right? So they will always be the case. So X is to be this one, and this correspond and X inverse, you can compute X inverse, and D will be, you know, just the diagonal, like this 1 1 1. So it will be 0 1 1. Okay, as a diagonal. Okay, all the other part are 0. Okay, that's D. Okay, so that's it. Okay, so I think we will stop here. Okay, and it's about time for the quiz. Okay.